everybody's here to hear about machine learning. You really just stay here and listen and hear about that. My name is Sam, and Bram was kind enough to invite me to give this talk. So yeah, I'm going to tell you a little bit about my experience with using machine learning and cybersecurity, because it's not that common still to find machine learning and cybersecurity applications. And I found a lot of people are interested in what those use cases are and how we actually make that all work. Let's see if I can understand how this goes forward. So,
Did you talk just a touch louder? Just like a machine bed right here.
Yeah. Okay. So I'm going to go over some basic definitions, and I will check with all of you that you know what I'm talking about before I explain it too much. But then I'm going to talk a little bit about how machine learning models actually are built and how they get shipped in a production environment, and then how we evaluate whether it's actually doing what we expect it to do. And there will be plenty of time for questions, so please feel free. All right, a little bit of vocabulary. Somebody I was talking to who was a cybersecurity person asked me recently, what is ML? And I realized she didn't know it stood for machine learning. And I said, well, machine learning. And she still was confused. And I realized a lot of people now think, machine learning is bad. So I was thinking, well, how am I going to explain why it's not? And I asked ChatGPT. And I said, give me a funny answer. And it said, machine learning is like teaching a robot to ride a bike. It falls down a lot, which immediately made me think of this gift. I was thinking, oh God, here's this poor, terrified robot trying to understand. So then I asked ChatGPT, give me a better answer for machine learning. And it said, it's a subset of artificial intelligence that involves training algorithms to recognize patterns in data and make predictions or decisions without being explicitly programmed to do so. I thought that was actually a pretty good definition. So we're talking about software that can generalize on its own, essentially. So you show it examples of what you want it to look for, but it knows how to expand a little bit beyond that. Not a lot, a little. And I'm going to talk quite a bit about observability because it's so essential for machine learning. And I think all modern software, but especially for machine learning models that are deployed in production, you really need to know how the thing is actually working in the real world. And this is one of the ways that we do that. So I'm going to talk a little bit about how we build tracking and safe systems. We'll talk more about that. And I assume everybody in here is familiar with malware? Yeah, okay. So I'm going to use it kind of as a general term that includes everything: works, viruses, adware, ransomware, but narrow it down in specific models for specific types of malware. So you might have a different machine learning model for ransomware. And how many people are familiar with advanced persistent threats? Okay, so about half of them. So it's a specific term that refers to these prolonged, very sophisticated attacks, usually carried out by these well-funded, state-backed, often organizations. And it can range all the way from social engineering and phishing kinds of things to actually moving between systems and stealing data. So I'll talk a little bit more about how we build models to address these kinds of use cases. And you don't actually have to read this whole slide. I will share my slides, but this is a bunch of example use cases where we have successfully used machine learning to address what would be considered a range of advanced persistent threats. So everything from domain name generation to bot attacks, living off the land kinds of things. And these are all different kinds of techniques. Sometimes you'll find them combined in the same attack. So why use machine learning in cybersecurity? I think a lot of people are kind of initially resistant to it, and they're worried we're going to steal security engineers' jobs or, take away all the work for SOC analysts. But that's really not the goal. The main advantage is that we can use machine learning to do things faster and at larger scale. But also it's smarter than regular software. So we can automate all the boring stuff away. Anything where you would create a bunch of rules once you get past a certain number of rules, it makes more sense to build a single machine learning model. And it's basically just a smarter set of heuristics. But probably most importantly, if we can automate that stuff, then we free up our security researchers to work on the more interesting problems. So that's been my pitch to, we don't want to take anybody's job. That is not the goal at all. But cybersecurity continues to be more and more sophisticated and complicated, and there's more and more data to look through. So anything we can use that makes a security researcher's job easier is actually good. One of the biggest tools that we found most useful is anomaly detection. So this is a type of machine learning that knows how to model normal behavior and see when your system is in a happy state where nothing is going wrong, and then detects automatically if there's a big spike or a drop, things that humans can do easily by eye, but again, can do it in parallel more quickly. And then we can rank those anomalies by severity, and we can identify what features we think are contributing automatically. And this is an example of what we might see if we were looking at dashboards, completely fake. This is not it. But we would say, okay, everything's okay, basically looks like a flat line. That's how we would set a baseline of this is the normal amount of noise we see in our system. We might see some anomalies that we know are not emergencies, right? Somebody failed to log in a few times, but they eventually remembered their password and all is well. Or we might see a huge spike that indicates a denial of service attack or something very strange is going on. And sometimes we'll see a whole bunch of anomalies, and then the interesting question is, are they related to each other? Another type of machine learning we use a lot in security is traits. So on the left here, I've got an example of a decision tree where you're kind of following the same kind of logic again that a person would if you're going to make a decision. So at the top, you would say, I'm going to look at cars that are red. If they're red, I want to know if they're new. And if they are, then I'm going to be interested in buying it. And if you decided, okay, maybe I don't want only red cars, let's also look at yellow cars. If the car is yellow and it's a Ferrari, then I might be interested in buying it. So this kind of semi-complex logic we can very easily capture in a model. And the interesting thing about these is that we don't have to decide the splits. We can dump a whole bunch of data in and have the computer help us decide where are the branch points to help us categorize examples of things that we see. And we use this type of thing in a slightly more sophisticated application where we would build a whole forest of trees, so not just one, but lots of them, and it's called a random forest because the point where you do the first split is randomly chosen from all of the different variables that you're interested in. And that is more useful for more complicated scenarios like malware. So you can start to get these more what they call uneven decision boundaries, right? And that lets us basically very quickly show the computer a bunch of data and say, okay, now identify all the patterns in here, rip all these things into probably malware, probably not. And it helps us tell it, every time you make a mistake, do another round, and weight your mistake more heavily so you can think more carefully about what you can do next time. So when we actually want to detect malware with machine learning, we start by doing static analysis. We don't run the malware in order to do this. So we're pulling out features of the files, and then we're going to compare with observations made by other vendors, usually. We crowdsource. There are a couple of clearing houses, basically, where all of the malware vendors compare notes. And then we would build a model that can recognize patterns and make an informed guess, and put a weight on how confident we are about that guess. So what we end up with is an application that will sit on your machine and it will run anytime a file gets downloaded. And then check to see if you think this is malware or not. So here's my little drawing. Thank you, Internet, for somebody else's art. Here's your person sitting at the computer. These little monsters up here are your malware. And then the file contents are going to be opened up by the application. In the background, what we're doing on our side, we've got data pipelines that are pulling from these third-party sources like MySQL and Recursive Labs, as well as other data, whatever other observations you want to pull in to train the model. And then we have, modern software engineering practices, so CI/CD, logging, tests, all that good stuff, to help us validate that all of our data is clean, that our model is working reproducibly. And then we usually back up the model with exception lists and allow lists. Continuous integration, continuous delivery. So it's an automated system for running your tests, basically. So where do models come from? This is about what people think. Many people think it's just that. So, the most important thing, I think, is to understand when is the right use case for machine learning and when is not. If you have a problem that is too complex for simple heuristics, that's usually a time when you want to use machine learning. You have enough data is the key thing, right? You need to have examples of both malicious and benign, whatever the thing is that you're trying to look at. And then you want to have a supervised model. The data has to be very clearly labeled, so you need to know what's malicious and what's not. That's not necessary if you're doing deep learning, but if you do want to do a kind of neural net deep learning sort of approach and you have unlabeled data, you still need to know that you have examples of both malicious and benign in that data set that you want to train on. And then you want to choose a model type. And this is partly science. There's similarities between different model families, but to some extent you just have to try it. And we usually do try a few different model types because sometimes the trade-offs are not immediately obvious on any given data set and any given use case. And then when we train the model, it literally is just showing it data. So we split the data into what we want to train on, and then we save out a test group that we're going to validate against that the model has never seen. And that's the way to objectively tell that the model is doing what we want. We have very clear criteria, which is usually statistical, based on is the model performing to the degree of accuracy that we require. And finally, we have to have monitoring. So we have telemetry or logging, usually both, to tell us if the model is performing the way we expect. So if we're going to build a model to detect an advanced persistent threat, this is actually kind of a tricky case because we don't have an easy way to get data often. So we can start by mocking up an attack the same way a security researcher would. So we spin up a few virtual machines and literally have one of them attack another one, right, and log everything. And if we know what kinds of techniques we want to be able to detect, this is a good starting point. And then we start by creating rules that we would associate with behaviors we know are bad. So, for example, we're pretty sure that this person is not who we think they are because their usage patterns don't match their usual usage patterns. If we only ever see them log in between 9 and 5 on weekdays, and we suddenly see a login with a huge download on a Saturday night at midnight, that starts to look a little bad. We also look for obvious things like, oh, they installed software that we know is malware. And then one of the tricks that we found effective is to just run those rules in production and use that to label the data on real data from real customers. And that gives us a way to have labeled data to build supervised models from. So this helps us bootstrap basically from unlabeled data to a model we can actually work with. And last but not least, when we get ready to actually ship a model, we're going to package it up with a bunch of metadata. So usually this means we're going to compress it and encrypt it. Usually you want to know the version, what are all the files that are in there, have a little bit of data so that when you install the thing on your customer's machine, you can double check that the installation worked correctly. You're going to send it out as an artifact, often it's an email, or you're going to expect your customer to go to a download site. And if it's a plugin, then the user is going to have to activate the installation themselves. So we're going to have to alert them that the new version is out. And if we want to know how well our models are doing in the real world, start with dog fooding. We're all running our models on our own machines all the time. Often we'll do a canary test, which is a way of releasing to a small number of customers and give us feedback, or do a silent release. The models running in the background. We're still getting logs and stuff. They're not getting those. Let me look at all that telemetry and make sure the model's performing out in the real world the way it did in our little sandbox testing areas. And last but not least, we have third-party testing. So if you're doing malware, for example, the antivirus consortium, ABC, does testing on data that our model has not seen before. So we don't necessarily know how well it's going to perform on that data set, but if we did our job correctly and trained the model on a wide enough variety of things, it should perform well in those tests. And I'm going to stop there and thank Brianne for this invitation, all of you for coming, Giphy for all of the fun animations, and OpenAI for ChatGPT's definitions. But yeah, I've worked with a lot of people on these kinds of things over the years, so happy to take questions.
Thank you for the introduction. You alluded to AI or machine learning is the downfall of the universe. And there's quite a lot of concern about algorithm fairness with AI. Yeah. So I'm wondering, and I've been trying to think about whether it applies in the cybersecurity space. Do we have some instances where algorithm fairness is a problem in cybersecurity? Or you're looking at attackers, so we really don't have problems with demographics or underrepresented people or any of those kind of things. Do you have any thoughts on that?
Yeah, so on the question of whether cybersecurity models are fair or not, I would say one of the big questions I've run into is people do use a lot of heuristics to assume whether something might be bad or not. The one I've seen the most is geographic, right? Certain kinds of software that isn't signed, you may or may not just block it. If it's not signed and it's from one of these 5 or 6 countries, it's probably getting blocked. And I'm not sure that that's completely fair. I think, like all other machine learning fairness, the key is to do a lot of data quality and really look and see what are the assumptions we're making before we build the model. Because the model is 98% data. The actual algorithm is just a tiny piece. If you saw these trees, they're not smart. Right? They're just trying to group things. So all of the assumptions that go into the model come from us, which means we have to examine what are our biases.
Geographic location is the one that stands out the most.
Geographic, whether something is signed or not, are 2 big ones that I've seen a lot. And I've seen, individual developers often don't have the means to deal with getting their stuff signed, or maybe their certificate expired and they just haven't dealt with it. So, those are just 2 examples I can think of off the top of my head. I'm sure there's plenty of others.
So my question is specifically more towards using ML in infrastructure security, or maybe even network security. Let's just stick to networks here. So traditionally for network security, as a supplement to the existing security controls, you have the telemetry that we already talked about, right? And you capture specific monitoring data. Based on that, you assess how your security infrastructure is doing, right? And while I understand the definition of ML, and I also understand the definition of monitoring, but I'm still a bit confused on why would I use ML if my monitoring infrastructure, my telemetry infrastructure is already gathering me all the necessary events I need to be working on or rather be alerted on. In what situation would I truly use ML for infrastructure?
So it would make it wildly much easier to identify anomalies. Right? For you to go and look through all of those dashboards and hours of telemetry by eye takes forever. But we can spit all that data through the model all the time. So it can flag for you if something looks anomalous in a much more efficient way.
Yeah, sure enough. But you could also have I'm not suggesting, I'm not against ML. I'm just trying to, because we don't, like, the industry which I'm working, we don't really have ML, but we're exploring ML and AI for it. Yeah. And I'm just trying to understand that if I already have a platform which does this analysis of pulling events and logs from different monitoring components and analyzing it for me and providing those anomalies with, or rather flagging those anomalies, would I truly need an ML in that situation?
It probably is using ML on the backend. Right? I mean, I think
It's not ML, correct? Well, the way it's shown is like yeah. And you could essentially automate so much of it, right? It clearly is going to take a lot of time, effort, resources to build that type of platform. But you could certainly do that. So that's essentially that's my confusion. Like, should I really get on that ML bandwagon when I already have an existing platform which does that post analysis for me, flags anomalies, right?
Right, well, that's what I'm saying. Anomaly detection is a form of machine learning.
Okay.
Yeah. So to some extent, you're already using it. It is just a slightly more sophisticated type of automation.
Which is not, it just not like fancy ML name. Okay.
Well, so defining an anomaly it's an NP hard problem in computer science, right? So figuring out the size of the window is basically impossible. You can only estimate it and iterate on it. That's why it's machine learning. If you could just set a rule and say, like, an anomaly is always going to be this size and it's always going to be this width, you wouldn't need machine learning, but it doesn't work like that. Right? Sometimes the scope is very big, sometimes it's wide. So that's one aspect of it. The other thing is finding those correlations. Typically that's done with machine learning also. So combining those data sets together, there are many different ways to do that. But it could potentially save you a lot of time of digging through. And you have some hypotheses basically that the software would provide you as a security researcher and dig deeper on all of those.
Thank you. Have you tried this model at all on SCADA or other OT type systems? I'm in manufacturing.
I have not, but I have other friends who have worked in that area.
Are there any tools out there available to do this sort of thing, or is it all just what you guys have developed?
I believe there are tools specifically for that use case, but I don't know off the top of my head what the names are. Yeah. Great. Thank you all so much. This was great.
One more time, one more.
Yeah, sure.
Tied to your question, kind of got to it, the ML is, or AI is the big buzzword in marketing, and everything it says ML on it, that's like the things that make it sell. Right. But getting to like a regression, analysis, like some very simple statistical formula may be enough to say this is an anomaly.
Technically, a regression is also machine learning.
Right. So, can you give some thoughts on the difference between, what is machine learning beyond what we've been doing in the past, and what's this new machine learning that really is not just a marketing buzzword, but actually doing something new?
Well, I mean, so it's not just a marketing buzzword in the sense that I think it does add value, right? These features are useful. The newer deep learning ChatGPT kinds of things, we've now crossed a boundary in natural language processing where you can ask a question in something more conversational, like with ChatGPT. Hey, ChatGPT, give me a thing. And in that sense, it's a lot faster for everyone because you don't have to learn a complex, specialized query language anymore. Right? You can have another layer in between where it's a little more like talking to a colleague. And that kind of stuff is really helpful. It's also, again, it's able to process and take in much larger data sets than we can handle previously. So the scale at which we're able to absorb all of this knowledge has drastically improved with using GPUs. And I'm actually working on a project like this right now, just how do we speed up taking in very large amounts of data and scale out the data quality processing that we need to do. Because the better the data set, the better quality.
Do you have any suggestions on, like, I don't know, books, websites, whatever, to start with, like,
I really hate Splunk's anomaly detection. Like, it's so bad. We have an employee who lives in Korea. He works out of the Korea office, and every single day I get an alert that he has logged in from Korea. And I'm like, yeah, duh. So like, I would love to try some of this out with that garbage anomaly detection and just stop using Splunks.
Yes.
Where do you have suggestions on like where to start? I do not have the first idea of like model how I make it work.
Right. Well, you might not want to build your own, but there are other products that I can recommend. And yeah, and if you wanted to build your own, I can recommend books on that too. So. I will stop there. Well, I think I have my contact information here in case anybody wants it, but I'll also share my slide deck in the Slack. So.